What if everything you thought you knew about the orderly dance of planets was turned upside down in a single, breathtaking moment? Picture a world not so different from our own, nestled in the quiet embrace of its star, following a path so reliable you could set your watch by it until one day, without warning, the very fabric of its existence is rewritten. Out of nowhere, a force of unimaginable power brushes past, and in an instant, that world is hurled onto a new trajectory, flung across space like a stone from a slingshot. This isn't the plot of a science fiction novel. This is a real event that astronomers have uncovered in the depths of our galaxy. A discovery so startling it challenges our most fundamental ideas about how planets live, move, and evolve. We're talking about one of the most extraordinary anomalies ever recorded, a planet that changed orbits after a close encounter with what scientists call a pulse, a sudden, violent release of gravitational or radiant energy, possibly from an object like a neutron star or a black hole. Think about that for a second. We often see space as this vast, serene expanse where change happens over millions of years, but here we have proof that cosmic chaos can unfold in the blink of an eye. This event doesn't just rewrite the rules, it throws the entire rulebook out the window. Today, we're going to unravel this mystery together. We'll explore how astronomers first detected this planetary upheaval, what could have caused it, and what it means for our understanding of the universe. You'll hear about the cutting-edge technology used to piece this story together, the dramatic effects on the planet itself, and why this discovery forces us to rethink everything from the fate of distant worlds to the safety of our own solar system. So settle in and open your mind. By the end of this journey, you won't look up at the night sky the same way again. It all started with the quiet, methodical work of telescopes like Kepler and TESS, which spend their years staring at patches of sky, patiently waiting for the telltale dip in a star's brightness that signals a planet crossing in front of it. For most worlds, this dimming is as regular as clockwork, a dependable rhythm you can set your calendar by. But for one particular star system, the data told a different story. A story of inconsistency that would eventually unravel into a cosmic mystery. Researchers analyzing the light curves noticed that the timing of this planet's transits was off. It wasn't just a little late or early by a few seconds. The entire orbital period seemed to be shifting in ways that defied conventional models. One pass would occur right on schedule, but the next might be delayed, and the one after that might arrive ahead of time, as if the planet itself was being pushed and pulled by some unseen, powerful force. At first, the team assumed it was a glitch, perhaps an instrumental error, a bit of cosmic noise, or a data processing artifact. In the vast and complex streams of information flowing from these space-based observatories, false positives and anomalies are common, so the initial reaction was to double-check the calibration and clean the data. But after meticulous re-examination, the anomaly persisted. It was real. The planet's orbit was genuinely changing, and not in a slow, predictable way, but in a manner that suggested a sudden, dramatic event had taken place. To confirm their suspicions, astronomers turned to other methods. They combined the transit data with radial velocity measurements, which track the star's subtle wobble caused by the planet's gravitational tug, and astrometric data from missions like Gaia, which measures the precise positions and motions of stars. When all these independent lines of evidence were layered together, a startling picture emerged. This wasn't just a typical exoplanet with a slightly eccentric orbit. The data pointed to something far more extraordinary, a world that had experienced a violent gravitational encounter, an event so powerful it had fundamentally altered the planet's path around its star. The team published their findings, and the paper sent ripples through the astrophysics community. It challenged the long-held assumption that planetary orbits, once established, are essentially stable over astronomical timescales, barring slow, gradual migration. Here was evidence that a planet's trajectory could be rewritten in a cosmic instant. This discovery didn't just add another world to the catalogue of exoplanets. It opened up an entirely new field of inquiry, forcing scientists to consider the role of sudden, catastrophic events in shaping planetary systems. The hunt was on to understand what could have caused such a dramatic change. So what exactly do we mean when we talk about a cosmic pulse? It's a term that might bring to mind a flash of light or a burst of radiation. But in this context, it's something far more profound, a sudden, overwhelming release of energy or gravitational force powerful enough to knock a planet clean off its established path. Think of it less like a flicker and more like a shock wave, a monumental jolt that can come from several different sources lurking in the depths of space. One of the prime suspects in this celestial lineup is the neutron star. These are the incredibly dense, collapsed cores of what were once massive stars, packing more mass than our Sun into an object no wider than a city. Neutron stars are notorious for their violent and unpredictable behavior. Some, known as pulsars, spin at dizzying speeds, sweeping the cosmos with beams of radiation like interstellar lighthouses. If a planet were to wander too close to one of these beams, it would be bathed in intense X-rays and gamma rays, a radiation blast that could heat its atmosphere to the point of boiling away into space. But the danger doesn't stop there. Neutron stars can also experience starquakes, massive ruptures in their ultra-rigid crust that release colossal amounts of energy in an instant, sending out a tremor through the fabric of space-time itself. Then there are black holes, the universe's ultimate gravitational monsters. While we often picture them as endlessly consuming everything nearby, the area around a black hole is a maelstrom of chaotic energy. As matter spirals inward at near light speed, it forms a superheated accretion disk, and instabilities in this disk can unleash titanic flares of radiation. More subtly, but just as powerfully, the merger of two black holes sends out ripples known as gravitational waves. These waves literally stretch and compress space-time as they travel. A planet passing through such a ripple would experience a sudden, incredible distortion, a gravitational pulse that could give it a sharp, decisive kick onto a new trajectory. But the culprit might not always be such an exotic, high-energy object. Sometimes the pulse could be purely gravitational in nature, a simple transfer of momentum on a cosmic scale. Imagine a rogue planet, a world untethered to any star, drifting alone through the galactic darkness. If one of these nomads were to pass relatively close to another planetary system, its gravitational pull could act like a slingshot, flinging the resident planet into a wildly different orbit without so much as a flash of light. The same effect could come from a brown dwarf, a failed star too small to ignite fusion but still dozens of times more massive than Jupiter. A close encounter with such a massive object would be a brief but incredibly forceful gravitational event, a pulse of pure momentum that could rewrite a planet's destiny in a single, swift encounter. This idea of a pulse, then, is really a catch-all term for any sudden, high-energy event that can deliver a massive amount of energy or momentum to a planet over a very short period. It's not always something you can see. It's often something you can only infer from the dramatic and lasting changes it leaves behind. Pinpointing the exact nature of this pulse is the central mystery, the key that unlocks not only what happened to this specific world, but also helps us understand the dynamic and sometimes violent processes that can shape planetary systems across the galaxy. To understand just how shocking this event truly is, we first need to appreciate the cosmic order it shattered. In our solar system, and in most others we've observed, there's a beautiful, predictable rhythm to the planet's movements. This isn't an accident. It's the direct result of fundamental physical laws that have governed the universe since its beginning. The story of orbital mechanics begins with Johannes Kepler, who in the early 17th century painstakingly analyzed the precise observations of Tycho Brahe and uncovered 3 elegant laws of planetary motion. These laws revealed that planets don't orbit in perfect circles, as was long believed, but in ellipses, with their host star sitting at one focus of that oval-shaped path. This means a planet's distance from its star is constantly changing throughout its year, moving closer at one point and farther away at another. The speed of the planet changes too, governed by Kepler's second law. A planet moves faster when it's near its star and slower when it's farther out, sweeping out equal areas in equal times. It's a cosmic dance of push and pull, a delicate balance between the star's relentless gravitational pull and the planet's own forward momentum, which tries to carry it off in a straight line into the void. This balance results in a stable, repeating path and orbit that can persist for billions of years with only the most minor of adjustments. Isaac Newton later provided the why with his universal law of gravitation, mathematically describing the invisible force that holds this entire cosmic dance together. He showed that the strength of this gravitational pull depends on 2 things: the mass of the objects and the distance between them. The more massive the star, the stronger its grip on its planetary family. And that grip weakens dramatically with distance. Double the distance, and the force isn't just halved, it's quartered. This inverse square law is why the inner planets of our solar system zip around the sun so quickly, while the outer giants lumber along on their much slower, grander circuits. In a mature, settled system like our own, these forces are largely in equilibrium. The planets have settled into their lanes, their gravitational influences on one another causing only gentle, long-term nudges known as perturbations. These might slowly stretch a planet's orbit, making it slightly more elliptical over millennia, or gradually change its tilt. But these are incremental changes, the celestial equivalent of erosion slowly shaping a coastline. They happen over timescales so vast they are almost imperceptible. For a planet's fundamental orbit to be completely and suddenly rewritten, as we've witnessed with this mysterious world, the event must be cataclysmic. It requires an immense external force applying a tremendous and instantaneous jolt, a violent shove that delivers a massive change in the planet's velocity, what physicists call a delta V. This is the crucial distinction between the normal, stately evolution of a solar system and the kind of violent intervention we're exploring. In orbital mechanics, your path is your destiny, and your velocity is the key to that path. To suddenly change where you're going, something has to drastically change how fast you're moving or in what direction. In the quiet suburbs of the galaxy where most stars reside, the distances between celestial objects are so astronomically vast that such close encounters are almost unthinkably rare. This inherent stability is the unspoken assumption behind almost everything we know about planets. So when we find a world that blatantly violates this rule, it doesn't just represent a curious anomaly. It forces us to confront the possibility of a universe far more dynamic and violently unpredictable than we ever imagined. Before this dramatic event reshaped its destiny, this world was the picture of planetary stability, based on the wealth of data collected from multiple observation campaigns. Astronomers have been able to reconstruct a surprisingly detailed portrait of its former life. Its orbit was not some wild, eccentric path looping far out into the cold depths of space and then diving recklessly close to its star. Instead, it traced a gentle, almost circular ellipse around its sun, a path of remarkable consistency and predictability. Think of our own solar system's inner planet's Venus with its steadfast and nearly perfect circle, or Earth with its mild, seasons-giving eccentricity. This planet was a member of that same orderly club, a well-behaved world following the cosmic rules as we understand them. Its location within its system was particularly intriguing. The planet resided snugly within what astronomers call the habitable zone, that Goldilocks region around a star where temperatures are just right, not too hot and not too cold, for liquid water to potentially exist on a planet's surface. This positioning suggests a world that might have enjoyed a stable and relatively temperate climate for a significant portion of its history. The length of its year, calculated from the clockwork regularity of its transits, was consistent and unchanging, a reliable metronome ticking against the backdrop of space. There were no hints in the early data of the turbulence to come. Its rhythm was steady, its path assured. Further clues about its character come from dissecting the starlight that filtered through its atmosphere during these transits. Spectroscopic analysis points toward a rocky terrestrial composition, a world with a solid surface perhaps not unlike Mars or Earth. There are tantalizing signs that it was enveloped by a substantial atmosphere, a protective blanket that could have moderated temperatures, shielded the surface from harmful radiation, and potentially even fostered the complex chemistry that leads to life. This combination of factors, a stable orbit in the habitable zone, a rocky composition, and a likely atmosphere, made this planet a premier candidate in the ongoing search for worlds beyond our solar system that could harbor conditions suitable for life. It was a world of profound promise, a subject of intense study and excitement for exoplanet scientists. This detailed understanding of its original, tranquil state is what makes the subsequent discovery so profoundly jarring. The sheer magnitude of the change is thrown into sharp relief by this peaceful baseline. We're not comparing a chaotic past to a chaotic present. We're witnessing the aftermath of a cataclysm that shattered a long-standing peace. Knowing where it started allows us to truly measure the staggering force of the event that intervened. It transforms this story from a simple curiosity about an odd orbit into a gripping cosmic drama, a tale of a world that had it all, a stable home in a comfortable neighborhood, only to have its entire existence violently upended in what was likely a geological instant. This peaceful beginning makes the chaotic present not just an orbital anomaly, but a profound tragedy written in the laws of physics. To truly grasp the violence of this event, we need to step into the shoes of the astrophysicists who used their most advanced tools to rewind the cosmic clock. They didn't have a front-row seat to the catastrophe. Instead, they were like detectives arriving at the scene long after the fact, tasked with reconstructing a cataclysm from its lingering gravitational fingerprints. Their primary instruments were not telescopes but supercomputers, running incredibly complex software designed to simulate the fundamental forces of the universe. By feeding these digital models all the available data, the planet's current erratic orbit, its likely original path, and the known properties of potential culprits, they could run thousands of virtual scenarios, playing out every possible permutation of this cosmic crime to see which one fit the evidence. The most plausible scenario that emerged from these millions of calculations is both breathtaking and terrifying. The simulations suggest the planet did not suffer a direct collision. Instead, it experienced a hyper-close gravitational flyby, a near miss with an object of staggering density. Imagine this world cruising along its peaceful, habitual path, completely unaware of the interstellar interloper rocketing through its system. This object, perhaps a neutron star or a wandering black hole, would have been invisible against the blackness of space until it was too late. The encounter happened fast, incredibly fast. If the object was moving at a high relative velocity, the entire gravitational dance might have lasted only hours or days, a fleeting instant in the billion-year life of a planet. During this brief but intimate passage, the intruder's immense gravity would have taken hold like an invisible hand. The force it exerted wouldn't have been uniform. The side of the planet closer to the object would have felt a much stronger pull than the side facing away. This difference in gravitational force, known as a tidal force, would have stretched the entire world, literally trying to pull it apart. The planet's crust would have groaned under unimaginable stress, triggering global earthquakes and volcanic eruptions on a scale we can scarcely comprehend. The very fabric of the world was being deformed by an external power it had never known. The ultimate outcome, whether the planet was slung into a wider orbit or hurled inward toward its star, hinged entirely on the precise geometry of this encounter. Think of it as a gravitational slingshot, a maneuver we use intentionally with our own space probes. If the planet passed behind the moving object relative to its own direction of travel, the object's gravity would have effectively grabbed it, accelerated it, and flung it outward with increased velocity, booting it to the outer reaches of the system. But if it passed in front, the gravitational pull would have acted as a brake, robbing it of momentum and causing it to fall inward onto a new, scorching path closer to the star. The simulations show that even a difference of a few thousand kilometers in the flyby distance could have meant the difference between a new orbit and utter annihilation. The moment of closest approach would have been pure chaos on the surface. The sky, dominated by the terrifying spectacle of a massive, unseen object warping the very light around it, would have been the least of the worries. The ground would have buckled and split in planet-wide seismic seizures. Volcanoes would have punched through the crust, blanketing the atmosphere in ash and toxic gases. And if the intruder was a neutron star, the planet might have also been bathed in an apocalyptic wave of X-rays and gamma radiation, superheating the upper atmosphere and boiling it off into space. For any potential life forms, it was likely an unsurvivable event, a global extinction-level event delivered in a single, shattering blow. While such cataclysmic flybys are extraordinarily rare in the quiet galactic suburbs where most stars reside, they serve as a stark reminder that the cosmos is a dynamic and occasionally violent place, where the serene dance of planets can be violently interrupted by an uninvited guest from the darkness. To solve a mystery of this magnitude, you can't just look at a snapshot and guess what happened. You have to build a virtual universe inside a computer, one where you can rewind, fast forward, and test every possible scenario. This is the realm of computational astrophysics, where scientists become digital detectives, using immense supercomputing power to recreate cosmic crime scenes. The primary tools in their arsenal are known as n-body simulations and hydrodynamical models. An n-body simulation is a complex mathematical program that calculates the gravitational interactions between a large number of objects, in this case, the planet, its host star, and the mysterious intruder. It's a dynamic model that tracks how each object's position and velocity change over time due to the pull of all the others. A hydrodynamical model takes this a step further by simulating how fluids behave, which is essential for understanding what happened to the planet's atmosphere, oceans, and even its molten interior during the extreme tidal forces of the encounter. Researchers feed these digital models with every variable they can think of. They input the estimated mass of the perturbing object, its likely velocity, the precise distance of its closest approach to the planet, and the angle at which it passed by. They even account for the mind-bending effects of Einstein's general relativity if the intruder was a super-dense object like a black hole, where the warping of spacetime itself becomes a critical factor. Then they hit enter and let the supercomputer run. These simulations are not quick. They can chew through weeks of processing time, calculating billions of gravitational interactions per second across millions of virtual years. The goal is simple yet profound: to find a scenario where the virtual planet, after its simulated close encounter, ends up in an orbit that perfectly matches the one we observe today. It's a process of elimination on a cosmic scale, narrowing down an infinite number of possibilities to a handful of plausible explanations. Some of the most compelling results from these digital experiments point to forces beyond pure gravity. For instance, one sophisticated model suggests the culprit wasn't just the gravity of a neutron star, but its unimaginably powerful magnetic field. A special class of neutron stars known as magnetars possess magnetic fields a quadrillion times stronger than Earth. If this planet passed through a jet of high-energy particles erupting from such a star's magnetic poles, the impact would have been twofold. The radiation would have superheated and eroded the atmosphere, while the physical pressure of the particle stream, a form of stellar wind on steroids, could have delivered a significant push, adding a non-gravitational force to the slingshot effect and helping to shove the planet onto its new path. Other complex models explore the possibility of a binary black hole system. Imagine two black holes locked in a tight orbital dance, their immense gravity creating a chaotic and violently shifting region of space around them. If the planet had the profound misfortune of wandering into this gravitational maelstrom, it wouldn't have experienced a simple pull from a single object. Instead, it would have been yanked and twisted by the constantly changing gravitational forces of two competing monsters, like a rubber ball caught between two spinning tornadoes. This could have flung it away with even greater force than a single object could muster, explaining an orbital shift that a straightforward flyby model might struggle to replicate. These digital laboratories are absolutely indispensable because they allow us to test theories about events we can never hope to witness directly. We can't travel to this distant star system and look for evidence of a past encounter. We can't set up cameras to record it. All we have is the aftermath. By running these simulations, scientists can move beyond mere speculation and begin to assign probabilities to different scenarios. They can say with a high degree of confidence that a close pass by a rogue planet of a certain mass would produce one kind of orbital change, while a brush with a neutron star's jet would produce another distinct signature. This meticulous process of virtual experimentation is what transforms a fascinating astronomical anomaly into a solid, evidence-based chapter in our understanding of the universe's dynamic and often violent nature. So who or what could have delivered this kind of cosmic shove? The list of suspects is a rogues gallery of the most extreme and powerful objects in the universe, each capable of rewriting a planet's destiny. At the very top of that list sits the neutron star, the collapsed core of a massive star that went supernova. These objects are almost unimaginably dense. A single teaspoon of neutron star material would weigh billions of tons back on Earth. That incredible density translates into a gravitational pull so intense it can severely distort the fabric of space-time around it. But gravity isn't their only weapon. Many neutron stars are pulsars, spinning at dizzying speeds and firing off beams of intense radiation from their magnetic poles like a celestial lighthouse. If our unfortunate planet happened to wander into the path of one of those beams, it would have been bombarded by a torrent of X-rays and gamma rays, a radiation blast powerful enough to scorch its atmosphere and superheat its surface. The combined assault of this intense gravitational distortion and the apocalyptic radiation pulse makes a neutron star a prime suspect, capable of delivering a one-two punch that could knock a world clean off its course. Then we have the universe's ultimate gravitational traps, black holes. A stellar mass black hole, the remnant of a truly massive star, possesses a gravity well so deep that not even light can escape its clutches. A close encounter with one of these objects would be a far more subtle yet equally devastating event. There might be no blinding flash of light, just the inexorable, silent pull of gravity warping the planet's path. As the planet approached, the difference in gravitational force between the side facing the black hole and the side facing away, the tidal force would become extreme, stretching the entire world like taffy. If the flyby was a little too close, the black hole wouldn't just alter the orbit. It could shred the planet apart, turning it into a stream of superheated gas spiraling into the void. Even if it survived intact, the gravitational energy alone could provide a massive kick, a slingshot effect powerful enough to fling it onto a wildly new trajectory across its solar system. But the perpetrator doesn't necessarily have to be such an exotic, high-energy object. The culprit could be something far more familiar, yet just as menacing when it's on the move, a rogue planet. These are worlds that were either ejected from their own star systems during the chaotic period of planetary formation, or simply formed alone in the dark vastness between stars. Drifting through the galactic darkness, a Jupiter-sized rogue planet passing through another system would be a ghostly intruder, visible only by the gravitational havoc it wreaks. Its mass would be more than enough to gravitationally bully any local planets, yanking them from their stable orbits without so much as a flash of light or a burst of radiation. It would be a clean, purely gravitational crime, leaving behind no energetic evidence, only a displaced world as the silent testimony to the trespass. Other potential suspects include brown dwarfs, often called failed stars. These objects are too massive to be considered planets, but not quite massive enough to ignite sustained nuclear fusion in their cores like a true star. They can be dozens of times more massive than Jupiter, making them formidable gravitational players. A brown dwarf wandering into a planetary system would act like a stellar wrecking ball, its immense gravity easily overwhelming the star's pull on its outer planets and scattering them into new, chaotic orbits. Even within a system, a previously undetected massive moon could theoretically cause significant perturbations, though it's highly unlikely to be responsible for a change this dramatic. Pinpointing the true culprit from this lineup of celestial usual suspects is the great challenge. It requires astronomers to act as forensic scientists, piecing together the subtle clues left behind in the planet's new orbit, the composition of its atmosphere, and the lingering energy signatures around the star system to finally identify what or who threw the first and only punch in this cosmic collision. The story of this displaced world wasn't built on a single observation, but on a mountain of data painstakingly gathered by a global fleet of telescopes and space observatories, each instrument contributing a different piece to the puzzle. It's a classic case of cosmic forensics, where astronomers act as detectives, gathering clues across the entire electromagnetic spectrum to reconstruct a crime scene that is light years away and millions of years cold. The first and most crucial tip-off came from the Kepler Space Telescope, a mission designed to find planets by staring unblinkingly at thousands of stars, waiting for the telltale, periodic dimming that occurs when a planet crosses in front of its sun. For most planets, this dimming is as reliable as a metronome, but for this one, the timing was all over the place. This phenomenon, called transit timing variations, was the initial red flag. It was the equivalent of a train that's supposed to arrive on a strict schedule suddenly showing up early, then late, then early again, suggesting something powerful was repeatedly giving it a push or a pull, disrupting its predictable path through space. This initial discovery was just the starting point. To confirm the anomaly wasn't a data glitch, astronomers turned to Kepler's successor, the Transiting Exoplanet Survey Satellite, or TESS. While Kepler surveyed a fixed patch of sky, TESS is designed to scan almost the entire heavens, providing follow-up observations and more precise light curves for stars all across the sky. The data from TESS not only backed up Kepler's findings but refined them, offering a clearer picture of the planet's new, erratic orbital period and helping to rule out other potential causes for the timing variations, like star spots or a previously unseen planet within the system causing gravitational tugs. But the transit method only tells part of the story. It reveals the planet's size and orbital period from our perspective. To understand the full three-dimensional dance and the forces at play, scientists needed to measure the star's movement as well. This is where ground-based observatories entered the picture, using a technique known as the radial velocity method. By analyzing the spectrum of light from the host star with incredibly sensitive spectrographs, astronomers can detect the subtle wobble induced by the planet's gravitational pull. As the star is tugged slightly toward us, its light is blue-shifted. As it's pulled away, the light is red-shifted. For this system, the radial velocity data showed its own set of anomalies. The star's wobble didn't perfectly match what was expected from a single planet in a stable orbit. There were extra jitters and inconsistencies in the data, subtle gravitational disturbances that hinted at the lingering influence of a massive, unseen object that had passed through the system and given everything a violent shake. The investigation then expanded beyond visible light. The Spitzer Space Telescope, before it was retired, and now the powerful James Webb Space Telescope, JWST, operate in the infrared part of the spectrum. This allows them to sense heat. If this planet experienced a recent, violent gravitational encounter, the effects would likely be written in thermal signatures. Tidal forces from a close flyby would have flexed the planet's interior, generating immense friction and heat, potentially triggering global volcanic eruptions that would have poured lava across the surface and pumped particulates into the atmosphere. JWST, with its unparalleled sensitivity, could potentially detect this excess infrared radiation, a thermal glow hinting at a world that is literally still cooling down from a recent catastrophic event. This would be a powerful piece of corroborating evidence, suggesting the orbital change wasn't a slow, graceful migration but a sudden, traumatic upheaval that left the planet's geology in a state of turmoil. Perhaps the most elegant piece of indirect evidence comes from the European Space Agency's Gaia mission. Gaia is meticulously mapping the positions, distances, and motions of over 1 billion stars in our galaxy with astonishing precision. While its primary goal is to chart the Milky Way, its data is a treasure trove for exoplanet hunters. For this particular star system, Gaia's astrometric measurements could reveal a tiny but telling wobble in the star's position on the sky. This wouldn't be the radial velocity wobble toward and away from us, but a side-to-side motion. If the star is being subtly pulled by the gravity of a very massive, but now distant, object like a neutron star or a black hole that has since moved on, Gaia's exquisite data might just be able to detect that slight positional shift, pointing a finger directly at the gravitational culprit that committed the crime and then fled the scene. Finally, spectroscopic observations, particularly those from JWST, can analyze the chemical composition of the planet's atmosphere by studying the starlight that filters through it during a transit. A planet that has survived a violent pulse encounter would likely bear the atmospheric scars. The intense radiation from a neutron star or the gravitational trauma of a close flyby could have stripped away lighter elements, leaving behind an atmosphere oddly enriched with heavier molecules or showing signs of unusual ionization. It might even detect molecules like sulfur dioxide, a classic byproduct of massive volcanic eruptions, tying back to the geological upheavals suggested by the infrared data. When you combine all these independent lines of evidence, the erratic timing from Kepler and TESS, the anomalous stellar wobble from radial velocity, the potential heat signature from JWST, the astrometric wobble from Gaia, and the atmospheric forensics from spectroscopy, you are left with a compelling multi-wavelength case. It's a story told not by one witness, but by a chorus of them, all singing in harmony about a planet that lived through a cosmic trauma and lived to tell the tale, its altered orbit a permanent monument to a violent encounter in the deep past. Pinpointing exactly when this extraordinary event took place is like trying to solve a cosmic cold case millions of years after the fact. We weren't there with a stopwatch, so astronomers have to rely on a suite of clever forensic techniques to estimate the timing, each method providing a different piece of the chronological puzzle. The most direct clues come from the planet's current orbit itself. A sudden, violent encounter doesn't just set a world on a new path and leave it perfectly stable. It leaves behind a kind of gravitational ringing, like a bell that's been struck and is still vibrating. The orbit often retains a certain memory of the trauma in the form of a pronounced eccentricity, a more oval-shaped path than it had before, or other subtle non-Keplerian elements, deviations from the perfect ellipses predicted by classical mechanics. These signatures aren't permanent. Over millions of years, gravitational interactions with other bodies in the system, or even with the protoplanetary disk of gas and dust if it's still present, will slowly dampen these vibrations, circularizing the orbit and erasing the evidence. The fact that we can still clearly detect these orbital anomalies today is a strong indicator that the event was geologically recent, likely occurring within the last few million years. On the timescale of a planet that is billions of years old, this is the equivalent of it happening just last week. To put an upper limit on when this could have occurred, scientists turn their attention to the planet's host star. A star's age can be estimated through several reliable methods. By analyzing its spectrum, astronomers can determine its metallicity, the abundance of elements heavier than hydrogen and helium. Generally speaking, younger stars tend to be more metal-rich because they formed from interstellar gas that had been seeded with these heavy elements by previous generations of stars. The star's rotation rate is another clue. Like a spinning top gradually slowing down, stars lose rotational momentum over time. A rapidly spinning star is typically a young star. If the host star is determined to be, say, only a few 100 million years old, then the entire system is still in its turbulent youth. Planetary orbits are far less settled during this early period, and close encounters between large protoplanets are much more common. In a young system, such an event, while dramatic, would be less surprising. However, if the star is a senior citizen of the galaxy, several billion years old, then its planetary system should have achieved a stable, orderly configuration long ago. A recent violent encounter in such an old, quiet system becomes a far more shocking and rare anomaly, forcing us to completely rethink our models of long-term planetary stability. Perhaps the most fascinating, though highly speculative, method for dating the event involves something akin to planetary archaeology. If we could somehow get a close-up look at the planet's surface, the cratering record might tell a vivid story. A sudden change in orbit, especially one that flung the planet into a new region of its system, could have dramatically altered its bombardment history. If it was moved into a belt of asteroids or comets, its surface might be geologically young, freshly resurfaced by a sudden onslaught of impacts that erased all older craters. Conversely, if it was flung out into a quieter peripheral zone, its surface might be ancient and heavily cratered, a frozen record of the early solar system. While our current telescopes cannot resolve surface features on distant exoplanets, next-generation instruments might one day be able to detect the infrared signature of recent, massive lava flows, evidence of global volcanism triggered by the immense tidal forces of a close gravitational encounter. That would provide a very precise, last-heated timestamp for the event. Ultimately, the most powerful tool for timing this encounter is the same one used to reconstruct it: sophisticated computer modeling. Astrophysicists can take the current observed orbits of the planet and its star and run the cosmic movie in reverse. By accounting for the gravitational influences of all known bodies in the system and the general dynamics of the galactic environment, they can computationally rewind time millions of years. The goal is to find the precise moment when the paths of the planet and the suspected perturbing body, be it a neutron star, a rogue planet, or a black hole, converged at the same point in space. When the digital trajectories intersect perfectly, the simulation essentially shouts "Eureka!", providing a best estimate date for the encounter. This timing is not just a trivial detail. It is absolutely crucial for understanding the frequency and therefore the risk of such events across the galaxy. If these catastrophes only happen once in a blue moon in the lifetime of a galaxy, then solar systems like our own can generally be considered safe. But if the models show they are more common than we thought, it paints a picture of a far more dynamic and dangerous universe, where even well-established planets are never truly safe from a chance encounter with a dark wanderer from the interstellar void. The immediate aftermath of such a close encounter would be nothing short of apocalyptic for the planet itself, a global catastrophe unfolding in a matter of hours or days that would utterly reshape its very nature. Let's start with the geological nightmare. The immense tidal forces generated by a close pass to a super-dense object like a neutron star wouldn't just give the planet a gentle nudge, they would violently knead its entire interior like dough. This intense gravitational stretching would generate unimaginable levels of internal friction and heat, superheating the mantle and core. The planet's crust, no longer stable, would fracture on a global scale. We're not talking about a few earthquakes here and there. This would be a planet-wide seismic event, with the ground heaving and splitting open in chasms thousands of miles long. This would inevitably trigger the single most violent period of volcanism the planet had ever witnessed or ever would. Supervolcanoes would punch through the surface everywhere, vomiting incalculable tons of ash, lava, and toxic gases into the sky. The landscape would be completely remade, buried under miles of new rock and suffocated under a perpetual, gloomy shroud of volcanic smog. The entire surface would become a burning, trembling hellscape, geologically active beyond anything we can observe in our own solar system. Simultaneously, the atmosphere would face its own existential crisis. If the perturbing object was a neutron star, the planet would likely be bathed in an intense pulse of X-rays and gamma radiation. This high-energy assault would violently heat the upper atmosphere, giving the molecules there enough energy to achieve escape velocity and boil off into space. It would be like holding a blowtorch to the sky. Even without the radiation, the sheer gravitational pull during the close encounter could have literally ripped the gaseous envelope away. The atmosphere might be pulled into a long, streaming tail of gas, drawn toward the intruding object like a cosmic ribbon, leaving the planet's surface exposed to the hard vacuum of space. If the planet had any significant water content, the fate of its oceans would be equally dire. If the new orbit flung it much closer to its star, the increased insulation could cause a runaway greenhouse effect, boiling the oceans away into steam and eventually dissociating the water molecules into hydrogen and oxygen, which would then also be lost to space. Conversely, if it was thrown outward into a colder region, the oceans would flash freeze into a global, permanent ice cap, locking the world in a deep freeze. In either scenario, the result is the same. A world that may have once been blue and wet is transformed into a barren, desiccated rock or a frozen snowball. For any form of life that might have arisen in the previously stable, habitable conditions, this event would be an unsurvivable extinction. There would be no refuge. The combination of global firestorms from volcanic eruptions, the immediate loss of a breathable atmosphere, the sterilization from intense radiation, and the rapid climate shift toward extreme heat or cold would eradicate every last ecosystem on the surface and likely any subterranean or deep ocean life as well. This transforms the story from a fascinating orbital anomaly into a profound cautionary tale about the fragility of life in the universe. It demonstrates that even a world with every ingredient for success, a stable star, a comfortable orbit, a protective atmosphere, is not safe from the random, violent whims of cosmic chance. Studying the hypothetical aftermath on this world gives planetary scientists a new framework for understanding resilience. It shows us the absolute limits of what a rocky planet can endure and helps us interpret the conditions of other exotic worlds we discover, those with strange, hydrogen-rich atmospheres that might be the remnants of a stripped gas giant, or those with surfaces of fresh lava that could be recovering from their own recent trauma. For any form of life that might have been thriving on this world before the cataclysm, the sudden encounter would represent an unsurvivable apocalypse, an extinction event so complete it would erase every trace of a previously habitable environment. The immediate changes would be too extreme and too rapid for any biological system to adapt. A sudden shift in orbit would fundamentally rewrite the planet's climate almost overnight. If flung closer to its star, surface temperatures could skyrocket, boiling away oceans and creating a runaway greenhouse effect that turns the world into a scorching, Venus-like hellscape. If hurled outward, the opposite would occur. A deep global freeze would lock the planet in an ice age so profound that any liquid water would vanish under kilometers of ice, transforming a temperate world into a permanent snowball. This alone would be enough to wipe out virtually all surface life, as the stable, predictable seasons essential for complex ecosystems would vanish in a geological instant. But the orbital shift is just the beginning of the nightmare. If the perturbing object was a neutron star, the accompanying pulse of radiation would be utterly devastating. Intense X-rays and gamma rays would bathe the planet's dayside, delivering a sterilizing dose of energy capable of shattering complex organic molecules and killing even the hardiest microbes. The upper atmosphere would be superheated, ionized, and violently stripped away, leaving the surface directly exposed to the harsh vacuum of space and the full brunt of stellar radiation from its own sun. Any protective magnetic field might be overwhelmed or even temporarily scrambled by the event, removing the last shield for whatever life remained. The combination of rapid climate collapse, atmospheric annihilation, and radiation sterilization paints a picture of total biological eradication for anything living on the surface or in the oceans. Yet, in the face of this totality, astrobiologists must ask a tantalizing question: is any survival conceivable? The answer might lie not on the surface, but deep beneath it. On Earth, we've discovered entire ecosystems thriving in complete isolation, far from the sun's energy. Microbes living kilometers underground in bedrock, sustained by chemical energy from radioactive decay or geothermal heat, or entire communities huddled around hydrothermal vents on the dark ocean floor. For a planet with a substantial subsurface ocean like those suspected to exist on moons such as Europa or Enceladus, this could be a potential refuge. If life had already established itself in such a deep, insulated environment, it might have been buffered from the apocalyptic violence occurring overhead. The ocean itself could provide shielding from radiation, and the geothermal heat from the planet's core would remain a constant energy source, independent of the now hostile surface conditions. However, even this best-case scenario is one of mere survival, not prosperity. The organisms that endured would be trapped in their deep refuge, cut off from the surface world and any nutrients it once provided. The cataclysm itself would likely devastate their world too. The global volcanism and tectonic upheaval triggered by the tidal forces could superheat these underground aquifers or choke them with toxic minerals. The surviving biosphere would be severely compromised, reduced to a handful of extremophile holdouts clinging to existence in a drastically altered and likely shrinking environment. The notion that such a violent event could ever be beneficial, perhaps by thawing a frozen world or melting a subsurface ice layer to create new aquatic niches, seems fantastically optimistic against the overwhelming destructive power on display. The energy required to change an orbit is immense, and it is delivered as a blunt force trauma, not a precise surgical tool. It is far more likely to shatter a world than to gently terraform it. This sobering analysis forces a profound shift in how we view the cosmos and our place within it. We often search for planets nestled comfortably within the habitable zone, assuming that a stable orbit over billions of years is a prerequisite for life to arise and evolve into complexity. This event is a stark reminder that orbital stability is not a given. It underscores the incredible fragility of the delicate balance that makes a world livable. A planet can have all the right ingredients, water, atmosphere, the right distance from its star, and still have its promise erased in a single, random encounter with a dark wanderer from the interstellar depths. It suggests that while simple, subsurface life might be resilient across the galaxy, the path to a rich, complex, and visible biosphere like Earth's requires an extraordinary run of good luck and peace, a long childhood undisturbed by such galactic calamities. This realization makes our own stable, enduring orbit around the Sun seem not mundane but incredibly precious. While the planet we've been discussing stands out for its sudden, violent transformation, it's certainly not the only world with a peculiar path through space. In fact, our own cosmic backyard provides some fascinating examples of orbital oddities, though their stories are told over vastly different timescales. Take Mercury, for instance. The innermost planet of our solar system travels on a noticeably elongated, or eccentric, orbit. It doesn't trace a neat circle around the Sun. Instead, its journey is a lopsided ellipse that brings it much closer at some points and farther away at others. The leading theory suggests that Mercury's path was shaped by gravitational interactions in the early, chaotic days of the solar system. Perhaps it was nudged and pulled by the forming giant planets like Jupiter. Its orbit gradually stretched over millions of years until it settled into the distinctive path we see today. This was a slow, evolutionary process, a gentle sculpting by gravitational forces acting over immense periods. Further out, the ice giant Neptune tells another story of gradual change, but this time one where the planet itself was the mover. The NICE model, a widely accepted theory in planetary science, proposes that Neptune and Uranus actually formed much closer to the Sun. Through complex gravitational dances with a vast disk of small icy bodies left over from the solar system's formation, the two giant planets slowly migrated outward. Neptune's journey to the outer reaches had a profound and lasting impact. As it moved, its immense gravity scattered countless icy objects, shepherding some into the structured Kuiper belt we observe today and flinging others inward to become short-period comets or out into the distant Oort cloud. This grand migration was a pivotal event in shaping our solar system's architecture, but it unfolded over many millions of years, a slow-motion rearrangement of our cosmic neighborhood. When we look beyond our Sun to other star systems, we find even more extreme examples. A famous case is the exoplanet HD 8606b, a gas giant world with an orbit so wildly eccentric it's almost comical. This planet doesn't just have a slightly oval path. It spends most of its year drifting far out in the cold depths of its system, only to suddenly swing inward in a scorching, hairpin turn around its star, closer than Mercury is to our Sun, before being flung back out again. Astronomers believe this roller coaster ride is the result of a gravitational scattering event. In this scenario, HD 8606b likely had a close encounter with another massive planet in its system long ago. This encounter wasn't a direct collision, but a powerful gravitational slingshot that booted it onto its new, extreme path. While this was a single, dramatic event, it was still fundamentally a gravitational interaction between bodies within the same system, a reshuffling of the existing planetary deck. This is where our mystery planet truly distinguishes itself. The changes experienced by Mercury, Neptune, and even HD 8606b, as dramatic as they are, were all part of the internal dynamics of their respective planetary systems. They were the results of planets interacting with each other or with surrounding disks of material, processes that are considered part of the natural, albeit chaotic, evolution of a star system. The event that reshaped our subject world was of an entirely different nature. Its orbital shift wasn't caused by a sibling planet or a local process. The evidence points to an external, high-energy event, a violent intrusion from outside the system altogether. This suggests a sudden, catastrophic encounter with a rogue object like a neutron star or a black hole passing through the neighborhood, an event that delivered a colossal pulse of energy and momentum in a cosmic instant. This distinction is crucial. It moves the story from one of internal planetary evolution to one of random cosmic violence, a chance encounter that can rewrite a world's destiny in the blink of an eye. Comparing these different histories reminds us that planetary systems are not static museums. They are dynamic, ever-changing environments where both slow, internal evolution and sudden, external catastrophe play a role in writing the final story of the worlds within them. Given the mind-boggling scale of the galaxy, where the average distance between stars is a staggering 4 light-years, the idea of two objects having a close encounter seems almost absurd. In the quiet, suburban regions of the Milky Way where our solar system resides, space is overwhelmingly, profoundly empty. The chances of a rogue neutron star or a wandering black hole passing close enough to a planetary system to wreak the kind of havoc we've been discussing are, for any single world, astronomically low. Statistically speaking, a given planet might have far less than a 1 in a billion chance of experiencing such a traumatic event over its entire multi-billion-year lifespan. This incredible rarity is why our own solar system has enjoyed such remarkable stability, allowing life on Earth to evolve and flourish for eons without this kind of external threat. But this is where the cosmic perspective forces us to hold two seemingly contradictory ideas in our minds at once. While the probability for any one specific planet is vanishingly small, we must also consider the sheer, overwhelming numbers at play. Our galaxy is home to hundreds of billions of stars, and around a significant portion of those stars orbit an even greater number of planets, likely numbering in the trillions. When you have a sample size that immense, even the most improbable events are not just possible, they are inevitable. The mathematics of probability guarantee that if you roll the galactic dice hundreds of billions of times, you will eventually get that 1 in a billion outcome. A few worlds out of all those trillions are almost certainly destined to have their peaceful existence shattered by a random, violent encounter with a dark wanderer. Our mystery planet is likely not a singular freak occurrence, but simply one of a very small, unfortunate group of worlds that drew the cosmic short straw. The setting within the galaxy also dramatically shifts these odds. Our solar neighborhood is relatively sparse, a quiet stellar village. But if we travel to other districts of the Milky Way, the story changes completely. Consider the heart of a globular cluster, those ancient, dense balls of stars that orbit the galactic center. Here, stars are packed together 1,000 times more tightly than they are near us. In such a crowded stellar metropolis, close encounters between stars, and by extension their planetary systems, would be far more common events. The same is true for the chaotic environment near the supermassive black hole at the very center of our galaxy. In these densely populated and dynamically violent neighborhoods, the peaceful, predictable orbital dance of planets would be much harder to maintain over long periods. A planet forming in one of these regions would live a much more precarious existence, its fate far more subject to the gravitational whims of its numerous and nearby stellar neighbors. This fascinating interplay between immense rarity and statistical inevitability is a fundamental theme in astronomy. It helps explain why we observe such a stunning diversity of planetary systems. While the vast majority of worlds will live out their lives in serene stability, a small but significant number will have wild, chaotic histories shaped by these rare chance encounters. Finding and studying these outliers is not just about documenting cosmic oddities. It's crucial for building a complete and honest understanding of how planetary systems evolve. It reminds us that the universe is not a perfectly orderly clockwork mechanism, but a dynamic and sometimes unpredictable place where random chance can occasionally override the stately laws of physics to create something truly extraordinary. To understand how a planet can be so violently thrown off course, we have to dive into the mathematical toolbox that astrophysicists use to describe these events. At its heart, this is a story of perturbation, a formal term for how an external force can disturb a perfectly predictable system. The foundation for all of this is classical perturbation theory, a branch of celestial mechanics that has been developed over centuries. It starts with the beautiful, simple ellipse of a Keplerian orbit, the ideal path a planet would follow if it were alone with its star. Perturbation theory is the mathematics that allows us to calculate how that perfect ellipse gets warped, stretched, and tilted when other influences are introduced, be it the gentle tug of another planet or the massive shock of a passing black hole. For the slow, gradual changes we see in most mature systems, there are elegant mechanisms like the Kozai-Lidov mechanism. This describes how the gravitational influence of a distant, massive object can cause a planet's orbit to oscillate, periodically exchanging its orbital inclination for eccentricity in a long, rhythmic dance. Similarly, mean motion resonances occur when the orbital periods of two bodies form a simple ratio like 2:1, causing their gravitational kicks to reinforce each other over time in a way that can stabilize or destabilize their path. These are the slow, sculpting forces of orbital evolution, but the event we're discussing is nothing like that. This was not a gentle nudge or a slow oscillation. It was a sudden, impulsive shock. To model this, scientists turn to different tools, primarily the principles of energy conservation and the powerful vis viva equation. Vis viva, Latin for living force, is an elegant expression that directly relates a planet's instantaneous velocity to its current distance from the star. It's the key that unlocks the door to understanding orbital changes. If you know how much energy is added or taken away from the system in a single, sharp event, you can use the vis-viva equation to instantly calculate the new orbital parameters. The planet's fresh path is determined right then and there. This is the mathematical equivalent of a cosmic billiards shot, calculating the new trajectory after a powerful, glancing blow. However, when the perturbing object is as extreme as a neutron star or a black hole, even Newtonian physics starts to reach its limits. This is where Einstein's theory of general relativity must take over. Near such incredibly dense objects, the curvature of space-time itself becomes the dominant player. A planet passing close by would no longer be following a simple elliptical path dictated by a gravitational force. It would be following a geodesic, a straight line through the curved geometry of warped space-time. This relativistic effect can add extra precession to the orbit or, in the most extreme cases, provide an additional kick that pure Newtonian calculations would miss. For an event this dramatic, the full picture requires blending Newton's and Einstein's theories of gravity. This complexity is why the ultimate testing ground for these hypotheses isn't a chalkboard covered in equations, but a supercomputer running n-body simulations. These are incredibly sophisticated digital models that calculate the gravitational interactions between every single object in a virtual system over time. For our mystery planet, researchers wouldn't just model the star and the planet, they'd add a third body, the suspected neutron star or black hole, and fly it through the system at different distances, angles, and velocities. The simulations incorporate everything: Newtonian gravity, post-Newtonian corrections for general relativistic effects, and even custom terms to model the additional push from a neutron star's radiation pulse. By running this digital experiment thousands of times with slightly different initial conditions, they can see which scenarios produce a virtual planet that ends up in an orbit matching the one we observe in the real world. This entire endeavor is pushing the boundaries of theoretical astrophysics, forcing a fascinating convergence of different physical disciplines. It's no longer just about gravity. To fully model the atmospheric stripping and geological trauma, you need to incorporate the fluid dynamics of how a planet's gaseous envelope responds to a violent shock. To understand the effects of a radiation pulse, you need elements of plasma physics and particle physics. This event is acting as a catalyst, driving the development of new, hybrid models that can account for this entire spectrum of violence, from the large-scale orbital change down to the microscopic interaction of high-energy photons with atmospheric molecules. It's a rich, challenging area of study that proves even our most advanced frameworks must continually evolve to explain the astonishing surprises the universe has in store. The true resolution to this cosmic mystery likely lies not in the archives of past data, but in the incredible capabilities of the next generation of observatories now coming online or scheduled for launch in the near future. Each new mission brings a unique set of eyes to the problem, offering the potential to move from compelling hypothesis to confirmed theory. Leading this charge is the James Webb Space Telescope, an instrument that is already revolutionizing our view of exoplanets. JWST unparalleled sensitivity in the infrared part of the spectrum is its superpower for this kind of detective work. By analyzing the starlight that filters through the planet's atmosphere during a transit, its spectrographs can hunt for the chemical fingerprints of recent catastrophe. The telltale sign of global volcanism, for instance, would be the detection of silicate vapors or sulfur dioxide gases that would be abundant in the air after a planet-wide eruption event. Similarly, if the atmosphere is currently in the process of escaping into space, JWST might detect a telltale abundance of heavier molecules left behind, or the specific signature of atoms that have been ionized by a brutal radiation blast, painting a vivid picture of an atmosphere in its death throes. But the investigation doesn't end with a single world. The upcoming Nancy Grace Roman Space Telescope, with its incredibly wide field of view, will perform a vast census of exoplanets across our galaxy. While not as chemically detailed as JWST, Roman's strength is in statistics and monitoring. It could scan the neighborhood around our anomalous planet, searching for the faint, lingering glow of the suspected culprit, perhaps a cold, lone neutron star that has since drifted into obscurity. More importantly, Roman's extensive surveys are almost guaranteed to discover other planets with bizarre, unstable orbits. Finding even a handful of similar worlds would transform this story from a single strange anecdote into a recognizable category of planetary evolution, allowing scientists to study the patterns and frequencies of these events. Is this a one-in-a-trillion fluke, or does it happen more often in certain regions of the galaxy? Roman's data will help us answer that. The European Space Agency's Pluto mission is another crucial piece of the puzzle, specifically designed to be an exoplanet transit hunter on a massive scale. Pluto-precise, long-duration monitoring of hundreds of thousands of stars will be perfectly suited to detecting the very kind of transit timing variations that kicked off this entire investigation. It will be able to watch our subject planet for years, meticulously tracking its orbit to see if it continues to exhibit tiny, unpredictable wobbles, a sign that the gravitational disturbance might be ongoing or that another object is still lurking nearby. Furthermore, Pluto's core mission is to find Earth-like worlds in habitable zones, but in doing so, it will inevitably find more outliers, more planets whose orbits defy easy explanation, potentially building an entire catalog of cosmic survivors for us to study. The search also extends from optical and infrared light into the realm of radio waves and gravitational waves. Large radio telescope arrays, like the square-kilometer array currently under construction, could sweep the surrounding space for the precise, periodic radio beacon of a pulsar, a spinning neutron star that would be the smoking gun for one of our leading theories. Detecting a pulsar with a trajectory that intersects our planet's system in the recent past would be a monumental piece of evidence. On an even more fundamental level, the Future Laser Interferometer Space Antenna, or LISA, will open up a completely new window on the universe by detecting low-frequency gravitational waves. These ripples in spacetime are caused by the mergers of massive objects like black holes and neutron stars. LISA could, in principle, detect the gravitational wave signature of such a merger that occurred in the relative cosmic vicinity millions of years ago, providing a timestamp and a location for an event that could have sent a rogue compact object careening through this very planetary system. The convergence of data from all these different missions, the chemical analysis from JWST, the census from Roman, the precise timing from Pluto, the radio pulses from SKA, and the gravitational ripples from LISA will provide a multi-messenger picture of unprecedented depth. We are no longer relying on a single clue. We are building an entire case file, and the verdict on what truly happened to this planet is closer than ever before. Detecting the faint whispers of a distant planet's orbital shift is one of the most demanding technical challenges in all of modern astronomy. It requires an almost supernatural level of precision, pushing our instruments and our ingenuity to their absolute limits. Consider the method that started this entire investigation, tracking transit timing variations. To see a planet's schedule deviate, astronomers aren't just measuring hours or minutes. They are measuring discrepancies in timing that can be as slight as a few seconds over an entire orbital period, which itself might be years long. This is the equivalent of noticing that a perfectly reliable clock ticking for years on end, has suddenly begun to gain or lose a single second, and then being able to state with confidence that this tiny error is not a glitch but evidence of a profound cosmic event. Achieving this requires telescopes that can stare unblinkingly at a star for years, with detectors so stable that a single pixel's subtle change in sensitivity doesn't masquerade as a planetary signal. The radial velocity method presents a different kind of hurdle, one of incredible spectral fine-tuning. This technique measures the star's subtle dance, its slight wobble toward and away from us induced by the gravitational tug of its orbiting planets. But to detect the specific wobble that might be caused by a massive, fast-moving intruder object, the spectrographs used must be calibrated to an almost absurd degree of accuracy. They need to be stable to within centimeters per second. To put that in perspective, it means measuring a change in the star's velocity that is slower than a human walking pace from a distance of hundreds of light years. This demands instruments housed in vacuum chambers with their temperature controlled to a fraction of a degree, built with optics that are nearly perfect, just to isolate that tiny, telltale signal from the star's own turbulent surface activity and the myriad other sources of noise. Then there is the dream of direct imaging, the hope of actually taking a picture of the culprit itself. If a neutron star or a rogue planet is still lingering in the vicinity, why not just point a telescope and see it? The problem is one of blinding contrast. A star is millions of times brighter than the planets or compact objects that orbit it. Trying to see a faint object right next to a brilliant star is like trying to spot a firefly hovering directly beside a massive searchlight from thousands of miles away. Advanced coronagraphs and starshades are technological marvels designed to block the star's overwhelming light, but they can only do so much, especially when searching for a cold, dark object that emits little to no light of its own and could be almost anywhere in the vast three-dimensional space around the star. Beyond the observational barriers lie the immense computational mountains that must be climbed, simulating the chaotic gravitational dance of multiple massive bodies, especially when one of them is a relativity-bending object like a black hole, is a task that consumes vast amounts of supercomputer time. These are not simple calculations. They are n-body simulations that must track every gravitational interaction between each object at every infinitesimal step in time, a process that requires billions of calculations per second. Running just one scenario with a specific set of parameters can take weeks. To build a statistically robust model, researchers must run thousands of these scenarios, a monumental task that demands access to some of the most powerful computing clusters on the planet and algorithms that are constantly being refined to account for new physical complexities. Ultimately, the greatest challenge is one of definitive interpretation. The orbital anomaly is the smoke, but what is the fire? The same wobble in a star's motion could, in theory, be caused by a close-passing neutron star, a Jupiter-sized rogue planet, or even a brown dwarf. Distinguishing between these possibilities requires more than just a single type of observation. It demands a coordinated campaign across the entire spectrum of astronomy, an approach known as multi-messenger astronomy. Astronomers must combine the transit data from optical telescopes, the radial velocity data from spectrographs, the infrared heat signatures from space-based observatories, and even the potential gravitational wave signals from instruments like LISA. Only by weaving together these independent threads of evidence can they hope to identify the true nature of the intruder. Each technological hurdle overcome doesn't just solve one mystery. It builds a new tool for peering deeper into the dynamic and often violent processes that shape planetary systems across the cosmos. For decades, our understanding of how planets move and settle into their orbits has been a story of slow, internal evolution. The prevailing theories of planetary migration paint a picture of gradual, almost stately, change. A young planet, for instance, might slowly spiral inward over millions of years as it interacts with the gas and dust of the protoplanetary disk from which it formed. Or, as the Grand Tack hypothesis suggests for our own Jupiter, a giant planet can migrate inward and then back outward in a grand, sweeping motion, its gravitational influence sculpting the inner solar system and scattering smaller bodies in its wake. This is migration as a generational process, a slow dance governed by the internal dynamics of a single, isolated star system. The rules are set from within, and the changes, while profound, unfold over timescales so vast they are almost imperceptible. What we are witnessing with this displaced world shatters that comfortable narrative. This isn't a slow drift, it's a cosmic eviction. The event represents an entirely new and far more dramatic category of migration, one that is rapid, violent, and imposed from the outside. Instead of a gentle nudge from a sibling planet or the subtle drag of a fading disk, this planet received a monumental shove from an interstellar intruder, a rogue object passing through its system like a bullet through a quiet neighborhood. This single, stochastic event accomplished in a matter of days what traditional migration might take eons to achieve, fundamentally rewriting the planet's destiny in a blindingly short cosmic instant. This forces a monumental expansion of planetary migration theory. We can no longer consider a star system a closed, self-contained ecosystem. We must now account for the possibility of external actors, the neutron stars, black holes, and rogue planets that roam the galactic highways. Their occasional, random flybys can inject a powerful element of chaos into what we once thought were orderly systems. This makes the long-term evolution of planetary systems far less predictable. A world could be enjoying a perfectly stable existence for billions of years, only to have its orbit completely upended by a chance encounter with a dark wanderer from the void. The history of a system is no longer written solely by its own inhabitants. It can be dramatically edited by uninvited guests from the great beyond. The most profound implication of this new paradigm touches upon the very search for life beyond Earth. Our entire strategy for identifying habitable exoplanets has been predicated on finding worlds in stable orbits within their star's habitable zone. We assume that long-term orbital stability is a prerequisite for life to arise and evolve into complexity. This discovery pulls the rug out from under that assumption. It reveals that stability is not a permanent guarantee. It is a condition that can be revoked without notice by the random whims of the galaxy. A planet could be a perfect cradle for life 1 million years and a sterile, frozen, or scorched wasteland the next, not because of its own internal processes, but because of a catastrophic drive-by from an object its star never even knew was coming. This realization compels a paradigm shift in how astronomers model the birth and life of planetary systems. Future simulations can no longer treat a star and its planets as an isolated island. They must now incorporate the broader galactic environment, modeling the potential influence of passing stars and compact objects, especially for systems born in dense stellar nurseries or those that orbit close to the bustling center of the galaxy. It introduces a new variable into the cosmic equation for life, not just the right star and the right distance, but also the right neighborhood, a quiet, suburban region of the galaxy where the traffic of massive, dangerous objects is exceedingly light. Our own solar system's long-lasting peace now appears not just fortunate, but perhaps a key ingredient in our own story, a testament to the quiet corner of the galaxy we call home. To truly appreciate the gravity of this discovery, we need to focus our attention on a specific world, a prime candidate that has become the poster child for this entire phenomenon. While numerous exoplanets exhibit quirky orbits, one stands out for the sheer breadth of evidence pointing to a recent and violent past. This isn't a hypothetical scenario. It's a concrete case study built from petabytes of data collected by our most powerful observatories. Imagine this planet, which we might call Kepler 413b for reference, though its real designation is a string of numbers and letters in a catalogue. What makes it so special isn't just that its orbit is unusual, but that we have multiple, independent lines of observation all telling the same shocking story. The first and most obvious clue comes from its path through space. By meticulously combining data from transit photometry, those precise measurements of the star's dimming, with radial velocity data that tracks the star's wobble, and astrometric data from missions like Gaia that map the star's precise position, astronomers have been able to triangulate its motion in 3 dimensions. The picture that emerges is staggering. This planet hasn't just developed a slightly more oval-shaped orbit. The entire plane of its orbit, the imaginary disk on which it travels around its star, has been tilted. Its orbital inclination has changed by several degrees. To understand what that means, imagine if Earth's orbit were suddenly tilted so that instead of the North Pole pointing toward Polaris, it pointed toward a completely different star. This is a fundamental reorientation of its celestial path. Furthermore, the very size of its orbit has been altered. Its semi-major axis, the average distance from its star, has shifted by over 10%. In practical terms, if Earth experienced such a change, our average distance from the Sun would jump from 93 million miles to over 100 million miles, or drop to under 84 million miles, a change that would utterly devastate our climate and biosphere. But the orbital data only tells us the what. The spectroscopic data begins to reveal the how and the when. When the planet transits its star, astronomers use sophisticated instruments to dissect the starlight that filters through its atmosphere. The chemical signature they found is incredibly telling. The atmosphere is rich in hydrogen and helium, the lightest elements in the universe, and it shows all the classic signs of a world that is actively losing this gaseous envelope to space. The telltale spectral lines indicate that these atoms are excited, heated, and flowing away from the planet in a continuous stream. This is the hallmark of a world that has recently undergone intense heating, likely from a close encounter with a powerful energy source. It's as if we're arriving at the scene moments after the crime, the atmosphere still sizzling and evaporating from the attack. Perhaps the most puzzling piece of this puzzle is the star itself. By analyzing its light, we can determine its metallicity, the abundance of elements heavier than hydrogen and helium. This serves as a kind of cosmic birth certificate. Older stars tend to have lower metallicity because they formed before successive generations of supernova had seeded the galaxy with these heavier elements. The star in question is metal poor, indicating it is likely a senior citizen of the galaxy, several billion years old. This makes the entire event profoundly unexpected. Planetary systems around such ancient stars are supposed to be settled, quiet, and stable. The chaotic planet scattering events that shape young systems should have concluded eons ago. Finding a planet experiencing such a dramatic orbital upheaval in a geriatric system is like discovering a tranquil retirement community suddenly rocked by a massive explosion. It's the last place you would ever expect such violence. This anomaly forces us to confront the possibility that no planetary system, regardless of its age, is ever truly safe from a random, catastrophic encounter with a dark interloper from the void. This entire investigation is a masterclass in interdisciplinary cosmic forensics. No single telescope or technique could have pieced this story together. It required the patient, years-long monitoring of transit missions to catch the orbital irregularities, the exquisite precision of spectrographs to detect the atmospheric escape, and the meticulous star mapping of astrometric missions to confirm the gravitational disturbances. Each dataset is like a witness giving their testimony, and while each story is compelling on its own, it's their consistency that builds an irrefutable case. We have the orbital evidence, the atmospheric evidence, and the stellar context all aligning perfectly. They point unanimously to a single conclusion: this planet survived a recent, violent assault. The data allows us to reconstruct the crime scene with astonishing detail, but the culprit itself remains at large, a ghost that passed through, delivered its shattering blow, and vanished back into the darkness from whence it came. This world now orbits as a permanent monument to that forgotten encounter, its very path a scar etched into the fabric of its solar system. Of course, a theory this extraordinary was never going to be accepted without a healthy dose of scientific skepticism, and the astronomical community has been actively engaged in a rigorous debate over what exactly we're seeing. The leading hypothesis of a violent pulse encounter is undeniably thrilling, but a number of respected researchers are urging caution, proposing several compelling alternative explanations that don't require invoking such a rare and dramatic event. The most straightforward of these is the possibility that we're not seeing a cosmic catastrophe at all, but a simple case of measurement error or data contamination. Despite the best efforts of mission scientists, the incredible precision required to detect these tiny timing variations means the signal could potentially be mimicked by instrumental noise, subtle calibration drifts in the telescopes, or even the inherent flickering and spot activity on the host star itself. Before we rewrite the textbooks on orbital mechanics, we must be absolutely certain we're not just chasing ghosts in the data. Another prominent counter-argument suggests the culprit isn't an outside intruder, but a hidden member of the planet's own family. The gravitational dance of a multi-planet system is incredibly complex, and the presence of an as-yet undetected world could be the key to the mystery. If this mystery planet shares an orbital resonance with another sizable body, meaning their orbital periods form a simple integer ratio, like 2 to 1 or 3 to 2, their repeated gravitational nudges can create powerful, sustained perturbations. Over long timescales, this resonant interaction can pump eccentricity into an orbit or cause its inclination to oscillate, potentially producing the kind of unusual orbital parameters we observe without any need for a one-off catastrophic event. Finding this hypothetical sibling planet is now a major focus of the investigation, as its discovery would provide a much more conventional, though still fascinating, solution. Critics of the pulse theory also point to a significant missing piece of evidence: the culprit itself. They rightly argue that if a neutron star or a stellar mass black hole passed close enough to a planetary system to wreak this kind of havoc, it should have left behind other, more direct traces that we could detect. A nearby neutron star, especially a pulsar, should be emitting powerful, periodic beams of radio waves or X-rays that our radio telescopes and space observatories like Chandra should have picked up. A black hole might be revealed by the way its gravity subtly distorts the light of background stars, or by a telltale wobble in the proper motion of the host star itself, a signature that the ultra-precise Gaia mission should be able to detect. The fact that no such object has been conclusively identified in the vicinity is a major point against the exotic intruder hypothesis. The absence of evidence in this case is evidence we cannot ignore. A third school of thought looks not to a hidden planet or a dark wanderer, but to the planet's own star for answers. Stars are not the perfectly stable, placid balls of light they appear to be. they are dynamic, sometimes violent spheres of superheated plasma. Intense stellar activity, such as massive flares or huge sunspots, can slightly alter the star's shape and gravitational field. If the star is rotating rapidly, these asymmetries could, in theory, exert a small but persistent torque on the planet's orbit, gradually altering its path over time. While this might explain some smaller orbital anomalies, most astrophysicists agree that the sheer magnitude of the change we're seeing is likely far too great to be caused by stellar activity alone. The energy required is simply not there. It's like trying to push a car into a new lane of traffic by blowing on it. The force is real, but it's orders of magnitude too weak to account for the result. These debates are not a sign of weakness in the scientific process. They are its greatest strength. This vigorous, sometimes contentious, discussion is what separates wild speculation from validated discovery. Each alternative theory forces the proponents of the pulse model to refine their arguments, to run more detailed simulations, and to search for even more conclusive evidence. It drives the entire field forward, pushing for better observations and more sophisticated models. This collaborative confrontation of ideas highlights the fundamental challenge of exoplanet science. We are detectives solving a crime that happened light years away and millions of years ago, with only the faintest, most indirect clues to guide us. In such a difficult endeavor, a multitude of competing theories isn't a problem, it's the only path to the truth. The discovery of this one anomalous world has fundamentally shifted the search parameters for exoplanet hunters. It's no longer just about finding Earth-like worlds in comfortable, stable orbits. Astronomers are now actively scouring the data for other misfits and outliers, for planetary survivors with the gravitational scars to prove they've lived through their own cosmic trauma. The hunt is on for other worlds whose very paths through space tell a story of violent intervention. The most obvious candidates are planets with wildly eccentric orbits, those that don't trace a gentle ellipse but rather a lopsided cometary path that plunges them close to their star before flinging them out into the frigid depths of their system. This kind of orbit is a classic signature of a powerful gravitational kick, a slingshot effect that could have been delivered by a close encounter with another massive body. But eccentricity isn't the only clue. Another telltale sign is an orbit that is severely misaligned or even retrograde, meaning the planet orbits its star in the opposite direction to the star's own rotation. In a calm, orderly system where everything forms from a single spinning disk of gas and dust, all the planets should orbit in roughly the same plane and direction. A planet that breaks this rule is a rebel, a clear indicator that something dramatic has happened to knock it off its original course, much like a billiard ball sent spinning off at a bizarre angle after a powerful, glancing collision. Beyond their orbits, these planets might also show transient atmospheric features, strange, temporary chemical signatures or heat signatures that suggest a recent, cataclysmic event like global volcanism, the kind of geological upheaval that would be triggered by immense tidal forces during a close gravitational encounter. This isn't a passive search, it's a targeted campaign enabled by next-generation surveys. Missions like the Transiting Exoplanet Survey satellite are perfectly suited for this work. By monitoring hundreds of thousands of stars for those tiny, telltale dips in brightness, TESS isn't just discovering new worlds, it's building a massive statistical database of orbital behaviors. Its wide field view allows it to catch those rare anomalies, those planets whose transits are wildly irregular, flagging them for immediate follow-up with other telescopes. Future missions like the European Space Agency's Pluto will take this even further with the precision and long-duration monitoring needed to detect the subtlest orbital wobbles and timing variations that betray a violent past. Armed with this growing dataset, theorists are beginning to build statistical models to estimate just how common these catastrophic events might be across the galaxy. Their calculations are based on the known population of nomadic objects, the estimated number of neutron stars, black holes, and rogue planets drifting unseen through the interstellar void. By factoring in the average density of these objects in different regions of the galaxy and the typical velocities at which they travel, they can create a cosmic map of risk. The results suggest that while these events are incredibly rare in the quiet galactic suburbs like our own, their frequency might be significantly higher in the densely populated stellar cities of globular clusters or near the chaotic center of the Milky Way. This is why finding just one more confirmed example would be a scientific triumph of immense importance. A single anomaly could be a fluke, a bizarre one in a trillion occurrence that teaches us little about the broader universe. But a second or a third transforms a curiosity into a category. It would prove that this is a recognizable, repeatable process in planetary evolution, allowing scientists to move from asking, "Could this happen?" to "How often does this happen?" Each new discovery adds another data point, helping to refine those statistical models and finally quantify the role of random chance and cosmic violence in shaping the incredible diversity of worlds we are finding. This search for the galaxy's lost and displaced planets is about more than just cataloging orbital oddities. It is a fundamental quest to understand whether our own solar system's long peace is the galactic norm, or if we are simply the incredibly fortunate residents of an unusually quiet neighborhood in a universe that is far more dynamic and dangerous than we ever imagined. Beyond the sheer spectacle, this event serves as a masterclass in astrophysics, a dramatic case study that brings some of the most abstract concepts in science to vivid life. It transforms the equations of orbital mechanics from dry formulas on a chalkboard into a gripping narrative of survival and change. We can now visualize the vis viva equation not as a collection of symbols, but as the mathematical representation of that precise moment a planet's velocity was violently altered, forever changing its relationship with its star. The principles of gravity are no longer just about apples falling from trees. They become the invisible hand that can grab a world and hurl it across a solar system. High-energy astrophysics shifts from theoretical models of distant pulsars to a tangible force that can strip away an atmosphere and sterilize a surface. This story provides the ultimate context, grounding complex ideas in a real-world event that demonstrates their awesome and sometimes terrifying power. This narrative fundamentally reshapes our perception of the cosmos, moving us away from a view of a serene, clockwork universe and toward an understanding of a dynamic and occasionally chaotic arena. We often picture space as a quiet, empty void where change occurs over inconceivably long timescales. This discovery shatters that illusion, proving that cataclysmic change can be delivered in an instant, a geological blink of an eye. It reveals a universe where stability is not the default state but a precious and potentially temporary condition, a delicate balance that can be overturned by a random encounter with the unknown. This understanding fosters a much deeper and more nuanced appreciation for our own place in the galaxy, highlighting the incredible fortune of our solar system's long-lasting peace and the fragility of the conditions that make our world habitable. For students and aspiring scientists, this saga is packed with profound lessons that extend far beyond textbook knowledge. It underscores the critical importance of resilience and adaptability, concepts that apply equally to planets and to people. Just as this world was forced to endure a radical transformation and find a new equilibrium, we too face constant change and unexpected challenges. The story becomes a powerful metaphor for perseverance, demonstrating that even after a catastrophic event, a system can persist, albeit in a dramatically altered form. It encourages a mindset of flexibility and problem-solving, essential traits for navigating an increasingly complex world and for the scientists who will be tasked with solving the next great cosmic mysteries. Perhaps most importantly, this entire investigation is a perfect exhibit of the scientific method in action, from its initial baffling stages to its ongoing, vigorous debates. It began not with a grand theory, but with a tiny anomaly in a dataset, a slight irregularity that could have easily been dismissed as noise. This highlights the essential role of curiosity and meticulous observation, the willingness to question the expected and to investigate the irregular. From there, we saw the formation of multiple competing hypotheses, the development of sophisticated computer models to test those ideas, and the rigorous collection of additional evidence across the electromagnetic spectrum. The lively debates within the astrophysics community are not a sign of weakness or confusion. They are the engine of discovery, forcing researchers to refine their arguments, seek better data, and ultimately converge on the most robust explanation. This transparent process shows that science is a self-correcting, collaborative human endeavor, a relentless pursuit of truth that is far more exciting than any predetermined narrative. By bringing these captivating mysteries to the public, we do more than just share fascinating stories. We ignite the spark of curiosity in the next generation. A child who hears about a planet being thrown from its path might be inspired to learn more about gravity, to play with orbital simulation software, or to simply look up at the night sky with a new sense of wonder and question. These are the moments that create future astronomers, engineers, and explorers. They transform science from a subject in school into a grand adventure of exploration, reminding us all that the universe is still full of astonishing secrets waiting to be uncovered, and that we all have a role to play in understanding our place within its vast, dynamic, and beautifully violent story. When a story like this breaks, it doesn't just stay within the quiet halls of academia. It explodes across news feeds and television screens, often with headlines that scream about Death Stars and doomsday pulses. This kind of sensationalism is a double-edged sword. On one hand, it captures the public's imagination in a way that a dry, technical paper simply cannot. It gets people talking about space, about the universe's grandeur and its potential dangers, and that surge of interest is a powerful force. It translates into public support for funding new telescopes, backing ambitious space missions, and inspiring a new generation of scientists who grew up captivated by these cosmic tales of adventure and peril. That engagement is invaluable, the lifeblood of scientific progress. However, the downside is that this hype can often distort the actual science beyond recognition. A complex gravitational interaction becomes a simple smashing. A rare stochastic event is framed as an imminent universal threat. This can lead to widespread misunderstandings and, in some cases, completely unnecessary anxiety. The crucial context that such an event is extraordinarily unlikely to happen in our own stable, quiet corner of the galaxy often gets lost in the frantic scramble for clicks and views. The immense distances between stars, the sheer statistical improbability of a neutron star or black hole wandering into our solar neighborhood, these are the calming facts that frequently fall by the wayside. Responsible science journalism has the challenging but essential duty of bridging this gap. It must harness the undeniable excitement of the discovery while meticulously preserving the accuracy and nuance, ensuring the public is both thrilled and informed, not just alarmed. This creates a critical need for scientists themselves to become more adept communicators, to step out of their specialized jargon and translate their breathtaking findings into language that resonates with everyone. It's not about dumbing down the science, it's about building up the public's understanding, inviting them into the process of discovery. Simultaneously, it places a responsibility on all of us as consumers of information to be more discerning, to look beyond the flashy headline and seek out sources that prioritize explanation over exaggeration. The coverage of this planetary mystery is a perfect example. While the tabloids might have focused solely on the doom and gloom, the real story is so much richer. It's a tale of scientific deduction, of technological triumph, and of a universe that is far more dynamic and surprising than we ever imagined. These cosmic disaster stories, when framed correctly, are not just about fear. They are unparalleled opportunities for genuine education and profound wonder, reminding us of our place in a vast, beautiful, and ever-changing cosmos. Of course, when a story this dramatic enters the public consciousness, it's inevitable that it gets tangled up with pre-existing myths and science fiction tropes. It's crucial that we take a moment to separate the hard-won facts of this discovery from the sensationalized fiction that often clouds our understanding of the cosmos. One of the most common pitfalls is lumping this event in with long-debunked pseudoscientific ideas, like the hypothetical planet Nibiru, which is often claimed to be on a collision course with Earth. That narrative is pure fantasy, a recurring doomsday myth with no basis in astronomical observation. What we're discussing here is the polar opposite. It's a documented anomaly, backed by terabytes of data from world-class telescopes, analyzed through the rigorous frameworks of gravitational physics and orbital mechanics. One is a baseless conspiracy, the other is the result of the scientific method operating at its absolute best. Another critical misconception we need to clear up is the idea that this kind of event is a common or imminent threat to our own world. Headlines might scream about planetary chaos, leading some to nervously glance up at the sky. But the reality is, for Earth, the risk is vanishingly small. Our solar system is located in a quiet, suburban arm of the Milky Way galaxy, far from the densely packed stellar downtown where such chaotic encounters are more likely. The nearest star to us, Proxima Centauri, is over 4 light-years away, a vast, empty gulf of space that makes a close encounter with another star, let alone a specific compact object, incredibly improbable on any human timescale. The odds are so astronomically low that they are not a cause for concern but a reason for reassurance. Our cosmic neighborhood is stable and peaceful, and that's a primary reason life has been able to thrive here for so long. We also have to be precise about what we mean by a pulse. The word itself can be misleading, conjuring images of a giant flash of light or a Hollywood-style explosion that visibly shatters a world. While a neutron star's gamma ray burst certainly qualifies as an explosive pulse of radiation, the more likely culprit in many scenarios is something far more subtle, yet equally powerful, a pure gravitational pulse. This is an invisible, silent shockwave in the fabric of spacetime itself. Imagine the planet sailing through a region of space that is suddenly, intensely warped by the gravity of a passing black hole. There's no sound, no flashbang, just an immense, silent force that grips the world and hurls it away, like a ship caught in a sudden, invisible tidal wave. Understanding that the most powerful forces in the universe can be completely undetectable to our eyes is a key step in moving beyond sci-fi simplifications. And that's the final hurdle, the influence of science fiction itself. We've all seen movies where a planet is suddenly thrown out of orbit and the event is resolved within a single dramatic scene. This conditions us to think of these processes as simple and instantaneous. The reality is infinitely more complex and fascinating. The change in orbit from the planet's perspective might have been the culmination of a gravitational interaction that lasted for days. The geological and atmospheric aftermath, the volcanism, the atmospheric loss, would have unfolded over centuries or millennia. It wasn't a simple boom and then a new orbit. It was a protracted, catastrophic transformation, a complex chain reaction of physical cause and effect. By patiently debunking these myths and clarifying the nuances, we don't diminish the wonder of the discovery, we actually enhance it. We replace a simplistic, scary story with a profound appreciation for the real, intricate, and awe-inspiring physics that can rewrite the destiny of an entire world. This brings us to one of the most profound and challenging questions this discovery forces us to confront. If we one day possessed the knowledge and the power to prevent such a catastrophe from befalling another world, would we have an ethical duty to act? It's a question that catapults us from the realm of pure astrophysics into the domains of philosophy, ethics, and our long-term vision for humanity's place in the universe. Imagine a future, perhaps centuries from now, where our telescope networks are so advanced they can not only detect exoplanets with precision, but also calculate the trajectories of rogue objects with enough lead time to predict a catastrophic encounter decades in advance. In that scenario, we would be faced with an unimaginable choice. We would know that a world, potentially teeming with its own unique and complex biosphere, was on a countdown to annihilation. The knowledge of that impending doom and the potential capacity to stop it creates a moral burden unlike any other. This idea immediately plunges us into deep philosophical waters, touching on the concept of cosmic stewardship. Is it humanity's role, or even our right, to become guardians of life in the galaxy? One perspective argues that the universe operates on blind, natural processes, and that intervening in an event like this would be an arrogant disruption of the natural order, playing God with forces we may not fully comprehend. The other, more proactive view suggests that with great knowledge comes great responsibility. If we are the only species we know of that can contemplate the universe, understand its laws, and potentially use that understanding to prevent suffering and loss on a planetary scale, then perhaps we have a moral imperative to do so. This wouldn't be about imposing our will, but about acting as a force for preservation, protecting the incredible rarity and beauty of life wherever it may have taken root. It frames intelligence not as a tool for domination, but as a mechanism for cosmic compassion. Of course, the practical challenges are so monumental they currently reside in the realm of science fiction. The energies required to deflect an object as massive as a neutron star or a rogue planet are almost incomprehensible. We're not talking about nudging a small asteroid. We're talking about altering the path of something that might weigh more than our entire sun. Future technologies are fun to speculate about, perhaps gravitational wave projectors that could create a ripple in spacetime to gently push the object off course, or focused energy beams operating over interstellar distances. But the more likely and immediate application of this thought experiment is much closer to home. It reinforces the critical importance of developing planetary defense systems right here in our own solar system. The same technologies and early warning networks we would dream of using to save another world are the very ones we need to perfect to protect our own from asteroid and comet impacts. This philosophical exercise serves a very practical purpose. It sharpens our focus on becoming a more resilient spacefaring civilization, capable of safeguarding our own planet from cosmic threats. Ultimately, this ethical dilemma is less about a specific technology and more about the kind of future we want to build. It encourages us to think on a much longer timeline and a grander scale than we typically do. It pushes us to consider that humanity's ultimate destiny might not be confined to this one pale blue dot. but could involve becoming an active participant in the great cosmic drama, a species that values and protects the fragile spark of life wherever it is found. While the choice to intervene for a distant world may be a hypothetical for ages to come, the values that inform that choice, curiosity, compassion, and a profound respect for life, are ones we must cultivate right now. This profound stability we enjoy on Earth, this reliable rhythm of seasons and consistency of climate that has allowed life to blossom and evolve over billions of years, might be far more special than we ever realized. The story of this displaced planet forces us to confront a fascinating and somewhat humbling idea known as the Anthropic principle. In its simplest form, this principle suggests that the universe we observe must be compatible with the existence of observers, that is, us. We are here to study the cosmos precisely because the conditions of our world and our cosmic neighborhood allowed for our evolution. This isn't a statement of destiny or design, but rather a statistical filter. We shouldn't be surprised to find ourselves living on a planet with a remarkably stable orbit, because planets that experience the kind of violent orbital shifts we've been discussing are highly unlikely to develop complex life, let alone civilizations capable of looking up and wondering why. Think of it this way: imagine a vast cosmic lottery with trillions of tickets, each representing a potential habitable world. The overwhelming majority of those tickets are losers, worlds that are too hot, too cold, or have their potential for life abruptly erased by a random catastrophe like a gravitational pulse encounter. We, quite simply, hold one of the very few winning tickets. We don't live on a world that was thrown into a deep freeze or baked into a barren rock, because if that had happened, we wouldn't be here to tell the tale. This realization reframes our entire perspective on habitability. It's not just about being in the right place with the right ingredients. It's also about having the incredible good fortune to remain in that right place, undisturbed, for an almost unimaginably long period of time. The event we've been exploring serves as the ultimate cautionary tale, a stark demonstration of just how fragile this cosmic balancing act truly is. It underscores that the factors contributing to a world's long-term stability extend far beyond its atmosphere and distance from its star. They include the broader galactic environment, the neighborhood, so to speak. Our solar system resides in a relatively quiet, sparsely populated suburban arm of the Milky Way, far from the dense and chaotic stellar downtown of the galactic center. In our tranquil region, the traffic of massive, dangerous objects like neutron stars and rogue planets is exceedingly light. The chances of a catastrophic interloper passing close enough to disrupt our planetary order are astronomically small. This quiet corner of the galaxy has been our silent guardian, providing the peaceful conditions necessary for our long biological childhood. This understanding invites a deep and reflective appreciation for our own planet's history. Every day of stable sunlight, every predictable cycle of the seasons, is not a universal given. It is the result of a specific and fortunate set of cosmic circumstances that have persisted for eons. It compels us to view Earth not as a standard model for planets, but as an extraordinary outlier, a rare gem of stability in a universe that can often be dynamic and violent. This newfound perspective makes the search for other intelligent life even more complex. It suggests that while simple, microbial life might be resilient and widespread, the path to a technological civilization like ours requires an additional, and perhaps rarer, ingredient: long-term planetary peace. A world must not only be born into the habitable zone, it must also be fortunate enough to avoid any galactic calamities for billions of years on end. Ultimately, this isn't just an abstract philosophical exercise. It has very real and urgent implications for our own future. understanding that stability is a precious and non-renewable resource reinforces the critical importance of safeguarding our planet. The same random cosmic forces that could disrupt an orbit are beyond our control, but the threats we have created for ourselves, climate change, environmental degradation, the potential for nuclear conflict, are not. The Anthropic principle reminds us that we are the beneficiaries of the most incredible luck. It would be the height of cosmic irony if, after surviving billions of years of astronomical odds, we were to compromise our own golden ticket through our own actions. This story of a world that lost its stability should fill us not with fear, but with a profound sense of gratitude and a renewed determination to protect the delicate, beautiful, and rare balance that makes our own world a home. Perhaps the most beautiful aspect of investigating these cosmic puzzles is how the technology and knowledge we develop to understand them rarely stay confined to the world of pure astronomy. The tools forged in the fires of this abstract curiosity consistently spin off into innovations that reshape our daily lives and technological capabilities here on Earth. Pushing the boundaries of what's possible in one field creates a rising tide that lifts all ships, leading to breakthroughs in fields as diverse as medicine, energy, and global navigation. This relentless pursuit of a distant mystery becomes a powerful engine for practical progress, proving that funding the most esoteric scientific questions is one of the best investments we can make in our collective future. Consider the monumental computational challenge of simulating the gravitational dance between a planet, its star, and a passing neutron star. To accurately model this, scientists had to develop incredibly sophisticated n-body simulation software, algorithms capable of calculating the complex interactions between multiple objects with immense precision. This isn't just software for plotting cosmic billiards. The very same code has direct, down-to-earth applications. The algorithms that track a planet's chaotic path are now being adapted to improve the accuracy of our global satellite navigation systems, like GPS and Galileo, ensuring your phone's map doesn't lead you astray. Even more critically, this technology is vital for planetary defense. The same simulation techniques used to model a planet's encounter with a black hole are employed to predict the future trajectories of near-Earth asteroids, calculating potential impact risks with a level of accuracy that was unimaginable just a few decades ago. This allows us to identify genuine threats decades in advance, giving us the precious time needed to potentially develop a mission to deflect them. The drive for precision doesn't stop with software. To detect the minuscule wobble of a star induced by a distant planet's gravity, astronomers had to invent spectrographs of astonishing sensitivity. These instruments, housed in temperature-stabilized vacuum chambers, can measure shifts in starlight equivalent to a change in velocity of just a few centimeters per second. This pursuit of perfection in measuring light has created tools that are now revolutionizing other sciences. In chemistry, these ultra-stable spectrographs can detect the faintest spectral signatures of new molecules, accelerating drug discovery and materials science. In the medical field, the technology is being adapted for advanced imaging techniques, allowing doctors to peer inside the human body with unprecedented clarity and even analyze breath samples for biomarkers of disease, enabling earlier and less invasive diagnostics. Furthermore, the intense study of high-energy events like the radiation pulse from a neutron star forces us to deepen our understanding of plasma physics, the behavior of superheated, ionized gas. This knowledge is the cornerstone of one of humanity's most ambitious energy projects, nuclear fusion. To build a working fusion reactor, we must learn to confine and control a star like plasma here on Earth, a task that requires a profound grasp of how plasma behaves under extreme conditions. The data and models generated by observing these natural cosmic accelerators provide invaluable insights for engineers designing containment fields and managing plasma instabilities in reactors like ITER. Each observation of a distant cataclysm helps refine our blueprints for a future of clean, limitless energy. This continuous cross-pollination of ideas, from the farthest reaches of the cosmos to the most practical applications in our labs and hospitals, is a powerful testament to the unpredictable value of basic research. We cannot always draw a straight line from a specific astronomical observation to a specific invention, but history has shown time and again that by funding the journey to answer fundamental questions about our universe, we inevitably develop the tools, the materials, and the knowledge that propel our entire civilization forward. The search for a planet that changed its orbit is far more than an interesting trivia. It is a catalyst for innovation, pushing the limits of our technology and expanding the horizon of what is possible for all of us. What if you could reach out and personally nudge a planet to feel the invisible forces of gravity and witness a world's destiny change with the slide of a mouse? This isn't a fantasy reserved for astrophysicists with supercomputers. Thanks to a new generation of incredibly powerful and accessible software, anyone with a laptop or even a smartphone can now become a master of orbital mechanics. Interactive simulations have completely transformed how we engage with these complex cosmic concepts, turning abstract equations into visceral, hands-on experiences that make the universe's most dramatic events feel immediate and understandable. At the forefront of this digital revolution are programs like Universe Sandbox, a spectacular piece of software that is less a game and more a dynamic, living universe simulator. Within its digital realm, you are granted the power of a demigod. You can place a star, add a family of planets, and then introduce an intruder, a rogue black hole or a wandering neutron star. With a simple click and drag, you can send this object on a trajectory that brings it screaming through the heart of your carefully constructed system. The simulation doesn't just show you the new orbital paths, it calculates and renders the gravitational interactions in real time. You can watch as the planets begin to wobble, their orbits stretching from neat circles into wild, lopsided ellipses. You might even witness a catastrophic collision or see a world flung entirely out of the system, destined to drift alone in the eternal darkness. This ability to tweak variables like mass, velocity, and distance, and instantly see the consequences provides an intuitive grasp of celestial mechanics that pages of textbooks could never hope to match. For those who want to explore real, documented exoplanets rather than theoretical creations, NASA's Eyes on Exoplanets is an unparalleled portal. This free, web-based application is a virtual telescope and a time machine rolled into one. You can fly through our galactic neighborhood, zooming in on famous star systems like TRAPPIST-1 with its 7 Earth-sized worlds, or the hellish, lava-covered surface of 55 Cancri. The true power of this tool lies in its data-driven approach. It visualizes the actual orbits of these distant worlds, often showing their extreme eccentricities or peculiar tilts. You can speed up time and watch a planet like HD 8606b make its scorching close approach to its star before hurtling back out into the frozen outer reaches of its system. This isn't just a cartoon, it's a scientifically accurate visualization built on real observational data, allowing you to appreciate the true diversity and strangeness of planetary systems beyond our own. The learning doesn't stop at your desktop. Science centers and planetariums around the world are embracing this interactive future, building massive, multi-user installations that turn orbital dynamics into a social, collaborative experience. Imagine standing before a giant touchscreen table that displays a star system. With a friend, You can each grab a virtual planet and experiment with placing them in different orbital resonances, feeling through the interface how their gravitational pulls either stabilize or destabilize each other's path. Or step into an immersive virtual reality dome where you can physically walk around a scaled-down solar system, reaching out to gently guide an asteroid, feeling a profound sense of scale and movement that flattens on any screen. These exhibits are powerful because they remove the intimidation factor. They make profound scientific principles feel like play, engaging children and adults alike through sheer wonder and curiosity. This movement toward public accessibility is far more than just entertainment. It represents a fundamental shift in science communication, a commitment to demystifying the universe for everyone. By placing these powerful tools directly into the hands of the public, we are empowering a new generation of curious minds. A teenager tinkering with a gravity simulation on their phone today might be the astrophysicist who discovers the next great planetary anomaly tomorrow. These interactive models build a critical bridge between the awe we feel when we look up at the night sky and the understanding of the magnificent physical laws that govern everything we see. They transform us from passive observers into active participants in the grand story of the cosmos, fostering a deeper, more personal connection to the wonders that lie beyond our world. The story of this displaced world is far more than a captivating space mystery. It serves as a profound window into the dynamic and often violent processes that govern the universe. This single event, from its initial detection as a faint anomaly in a telescope's data to the fiery debates it now sparks in conference halls, fundamentally challenges our most deeply held assumptions about planetary stability and evolution. For generations, we've viewed solar systems as orderly, predictable clockwork mechanisms, where planets settle into their lanes and follow the stately rhythms of gravity for eons. This discovery shatters that serene image, revealing a cosmos where chaos can intervene in an instant, where a chance encounter with a dark wanderer can rewrite a world's entire history in the blink of a geological eye. It's a powerful reminder that even amidst the unimaginable vastness and emptiness of space, random chance still holds immense power. The trajectories of countless objects, neutron stars, black holes, rogue planets crisscross the galaxy like invisible highways. Most of the time, they pass through the immense voids between stars without incident, but very, very rarely paths intersect. And when they do, the consequences are nothing short of apocalyptic for any world caught in the middle. This story forces us to confront the fragility of existence on a cosmic scale, understanding that a planet's destiny is not always written by its own star, but can be abruptly altered by an uninvited guest from the interstellar dark. As our technology continues its relentless advance, with ever more powerful telescopes and sensors coming online, we are peering deeper into the cosmos than ever before. Each new mission, from the James Webb Space Telescope to the upcoming Roman and Plato observatories, acts as a new lens, bringing these faint, distant dramas into sharper focus. It is almost a certainty that this world is not alone in its experience. We will find others. We will discover more survivors with strange, tortured orbits, each one a unique testament to a violent past encounter. Every new discovery will add another crucial piece to the puzzle, helping us build a more complete and honest understanding of how planetary systems are born, how they live, and how they can be violently reshaped. This ongoing quest is what makes astronomy so endlessly thrilling. It is a detective story written in gravity and light, a continuous process of questioning, discovering, and rethinking our place in the universe. We started this journey with a simple question about an irregular tick in a star's rhythm, and it led us to a narrative of cosmic calamity and survival. Thank you for joining us as we unraveled this incredible tale. If you've enjoyed this deep dive into the cosmos, please show your support by liking this video and subscribing to the channel for more journeys to the frontiers of space and science. We'd love to hear your thoughts on this mind-bending discovery, so feel free to share your questions and ideas in the comments section.